And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to be starting the final section of our notes. It's on everything else. Alright, so what we're going to do is we're going to start by discussing what happens when we have a factorial design that has more than 2 or 3 levels for all of the factors. They're going to be called prime level designs because, well, we're going to look at prime numbers because, well, they're the best ones to do, and we'll find out why in this lecture. We're also going to start our discussion on mixed level designs because sometimes when you have a factorial design, not all the factors have the same number of levels, and we have to account for that. What happens if you have a 2 and a 4 level factor, a 2 and a 3 level factor, and I guess, well, 2 and 5 and things like that, right? We have to consider all of these differences and how they interact with each other. And we also have to make sure that we do not have too big of a sample size, because if we've learned anything in this course, we've learned we're kind of lazy and we're cheap and we don't want to collect a lot of data. So we want to keep our sample size as small as possible, but still be able to test all of the things that we want to test. How are we going to do that? Let's find out in today's lecture. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we'll be starting the final section of my lecture notes, which is really the grab bag section that just includes everything else that we didn't talk about so far. I'm calling it non-regular, non-normal, and other designs, which should cover just about anything. Mainly the idea is that there's still a lot of other issues that can arise with designs when it comes to factors of various with more than 2 or 3 levels to them. When you're trying to have factorial designs that have mixed 2 and 3 or 2 and 4 levels. We'll also be looking at the so-called, I guess, non-regular designs like the Plackett-Bergman design, which is great for screening. And I think we might even have time for another bonus lecture in there. And we can cover some other different types of design settings. But today, what we'll be doing is we'll be extending the idea of the 2-level and the 3-level factorial design to other prime levels like 5 and 7. Now, the prime number aspect there is going to be important. We'll talk about that in today's lecture. And we might have time to start the following section, which will also be on factorial designs, but that will be on mixed level factorial designs. And that section can get a little bit more confusing when it comes to the idea of the orthogonal array. So perhaps we'll look at that a little bit today, and if not, we'll definitely tackle it in the next lecture. But for right now, we've got prime level factorial designs to do, so let's get into the notes and see how they work out. All right, so we'll be talking about today is the prime R, I guess, the prime level designs. And by that, I mean I want a design that is going to be an R to the K or R to the K minus Q factorial or fractional factorial design. Where R is a prime number. And that prime number aspect is going to be important because prime numbers give us finite fields, and that means we can, I guess, invert things. So, okay, I'm assuming that not everyone who's watching this has taken a course in, I guess, algebra. That is abstract algebra, and looked at fields and rings and finite fields and in particular. So we'll just kind of give a quick example of why I might want R to be a prime number. All right, so so let's do an example. If we have R is equal to 5, then that means that our arithmetic is going to be mod 5. So again, when we did the binary or the 2-level factorial designs, we were just, I guess, adding mod 2, and a lot of that was just multiplying plus and minus 1 because the two things are just equivalent ways to think about the same mathematical object. When we got to 3 level, we had that shorthand, right? And the shorthand notation for 3 level designs like A, B2 was effectively a shorthand that said we want to add A plus 2B mod 3. This is for 3 levels. So when we get to the idea of 5 levels, well, what we want is we want to have a multiplicative inverse. So basically, when working mod 5, we want a multiplicative inverse, which is the fancy way to say I want to be able to multiply every number by some other number and get 1, right? But I only have 4 numbers to work with, which is 1 through 4, since 0 is, 0. We don't have a multiplicative inverse there. So what I mean by that is that when, well, I already kind of set it up here, but we'll just say it again. When r is equal to 5, what do we get? Well, we get that 1 times 1 is equal to, well, 1 mod 5. Okay, that's great. Let's try 2. Well, 2 times what? I guess 2 times 3 is equal to 6, which is equal to 1 mod 5. So do you see where I'm going here? We have 3. 3 times 2 is also equal to 6, which is 1 mod 5. And 4 times 4 is equal to 16, which is also equal to 1 mod 5. Hence, if we look at our multiplication table mod 5, we have, I guess, well, I'm not going to include 0 because that's pointless. Of course, I can't do it. 1, 2, 3, 4, 5. 1, 2, 3, 4. Right, so we would have, if we multiply, do our multiplication table here, mod 5, we'd have 1, 2, 3, 4, 2, 3, 4. We would have 2 times 2, which again is 4. We would have 2 times 3, which is 6, which gets reduced to 1. 2 times 4 is 8, reduced will get us a 3. And similarly here, we get a 1. 3 times 3 is 9, reduced mod 5 is 4. 3 times 4 is 12, reduced mod 5 is 2. And lastly, 4 times 2 is 8, reduced mod 5 is 3. 4 times 3 is 12, reduced to get a 2 and a 1. And hey, if we look at that really closely, we might notice that we have a Latin square. Well, that's kind of fun. The Latin square returns again. Hooray. But the idea is that for basically every row and every column is going to have a 1 in it, which means that all of my elements have a multiplicative inverse. They have something that I can multiply them by to get 1. Now, the problem occurs if we don't have a prime number. If r is equal to 4, for example, well, what happens in this case? Well, what I'll do is I'll write out the entire multiplication table, since I think that's probably the best way to see it. In this case, we just have the elements 1, 2, and 3. Of course, we also have 0, but 0 times everything is 0, so I'm not going to include it in my table. So now, if I try to multiply everything out, I get 1, 2, 3, 2, 3. That's the easy one. 2 times 2 is 4. Mod 4 is 0. 2 times 3 is 6, and we get a 2 there. And then lastly, 3 times 3 is 9, which is 1. So the idea is that this is a problem. Basically, 2 does not have an inverse mod 4. And this is going to cause some trouble when we're trying to consider all of those different terms and interactions in our design. So we're not going to deal with that yet. This is a problem for later. Right now, we're going to stick up above with the prime levels, because if we have prime levels, we don't have to deal with that problem. But that's really just the explanation of why I'm kind of obsessing about the fact that R has to be a prime number, because otherwise things get a little bit trickier. I should point out that we'll put this in blue. Note R being a power of a prime, like 4 or 8 or 9 or 16, etc., can also work using something called Galois theory, which we are definitely not going to discuss in this course. But it's kind of fun to throw out some math jargon there, or terminology, I guess. Basically, if you have a power of a prime, you can also kind of make things work. We are going to look about this a little bit when we look at 4-level factors, but we're not going to get into like the gritty details of it. Now, the ones that really get messed up are the composite numbers that are not powers of prime, things like 6. So if you recall back from our Latin square discussion, there are no Greco-Latin squares of 6 by 6 Greco-Latin squares. And yeah, it's because when you have 2 times 3, it's just the algebra kind of gets all messed up. So most of the numbers that we have in like 1 through 10, say, well, not 1 is pointless, 2 through 10 are kind of things that we can work with. Typically, the number of factor levels is small. So we care about things like 2, 3, 4, 5. 6 can be a little troublesome. 7, prime number. 8, power of a prime. That's good. 9's good. 10's another troublesome one. But by the time we get to 10-level factors, that's unlikely to actually show up in a designed experiment. Typically, 2 and 3, 4 and 5 are the kinds that you would see in practice when it comes to the number of levels for a given factor. Anyway, yeah, so what do we want to do? Well, let's just talk about this in general. So we can construct an R to the k minus q design, much like before, with the 2 to the k minus q and 3 to the k minus q designs. And all we really need to do is we just need to, pick elements for the defining contrast subgroup, which are going to look like something like a summation. Here we'll say, okay, no, I don't want to sum that way. Sorry. This would be like summing I from 1 to k of, we'll say, ci xi mod r, where all I'm saying is I'm going to combine, this is a column in our design matrix, one of our factors, that is, this is a coefficient. So again, for example, we could have something like factor A plus 2B plus, I don't know, 4C or something like that, mod 5. So this would be like an A, B to the 2, C to the 4 interaction term. So all I'm saying is that really we can do the same thing. The math and the really just looking at all the combinations gets a little bit messy. So I'm not going to be like beating you over the head with like, oh, we have to try and do everything we did for 3 level with 5 level and 7 level and things like that, because it just gets really messy. But just to explain that, yeah, we could extend this to any prime level factorial design that we want. And yes, as a result, I'll say in an r to the k minus q design, we will, I guess, test, in this case, r to the k minus q minus 1 divided by r minus 1 different aliased groups of effects, which, i.e., rows in the ANOVA table. So it's always good to be able to remember to count and try to figure out what you should get. And again, in this case, this is the number of terms we should get. It turns out that that number should always be divisible by r minus 1, which is great, thanks to, again, to some, I guess, number theory or algebra or wherever you would discuss those topics. Yeah, so there's not really too much else to say in this case. It's really just we can extend it. So what I want to do is I want to look specifically at 5 and 7 level, because they're the most common ones you would see. They're still much less common than the classic, say, 2 to the k or 3 to the k designs, but it's good to at least look at them a bit and how you might, go about them in practice. So first of all, we'll say the next section, the next little mini section, is the 5-level design. I'll say, or the 25 run design. So I'm calling this 25 run design because basically the idea is that 5 to the 3 is equal to 125, which is already really big, which is big. Okay, it's big. It depends on how expensive it is to collect data, but we'll just assume that 125 is starting to get to be a big number. And three-way interactions, right? And if we considered this design, right, if we considered a 5 to the 3 factorial design, then I should say, which is big, also, we'll say main effects need 4 degrees of freedom, which is 5 minus 1. Two ways need 4 times 4, which is 16 degrees of freedom, to do all the different two-way interactions that are possible. Again, we can think of different types of contrasts in there. There's a lot of different ways that they can, in the two 5-level factors can interact. And if we go all the way up to 3 ways, well, they are going to need 64 degrees of freedom, which is, this is a lot. And these are hard to interpret. So the idea is, what's really the point? Why would I ever really want to consider higher interactions with 5-level factors when the interpretation the result, even if it's significant, may be completely uninterpretable? Right? You'll have these absurd, maybe polynomial contrasts. That would actually be a better situation. If you have an ordinal 5-level factor, at least you can have a polynomial contrast, which can give you an idea if your data is, say, increasing or parabolic or cubic as you move from the lowest to the highest level. If it's just purely categorical, then it can be even harder to find a good interpretation. So typically, the point I'm getting at, typically, we would just do a 5 to the k minus k minus 2 design, which requires 25 observations. And yeah, we're going to get probably a bunch of aliasing. It depends on how many, what k is, how many factors we're trying to shove into our 25 observations. But the idea is that, yeah, we don't really care about these higher order interactions, so let's try to alias as much as possible and test those main effects. Right, so I guess we'll do a quick little example of interactions, just so we can do it. If we have something like basically, yeah, what we'll do is we'll consider the table. So if I have my 25 run table, yeah, we're going to need a bunch of room for this. I'm going to go, I guess we need 1 through 5 would be, no, well, we can either do 0 through 4 or 1 through 5. I'm trying to think what the smartest way. We'll do 0 through 4, yeah. 1 or 0, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, etc., etc. I'm not going to keep doing all of these. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Okay, so we have our 2 columns, which are going to be our 2 main effects, and we're going to have observations y1, y2, all the way down to somewhere down here where we get y25, which I guess would have the values 5 and 5 here at the very end of our table. Now, if we break up the two-way interaction here, right, we're going to have our two-way interaction. This is going to be 4 degrees of freedom, 4 degrees of freedom, and then we're going to have, well, 16 degrees of freedom for A crossed with B. But that's going to break up into 4 different columns, AB squared, AB cubed, AB to the 4th. Yes, and these are each going to have 4 degrees of freedom associated with them. And like I said, these interactions may be extremely hard or completely impossible to interpret. So what we can do is we can alias them with another factor, another effect that we might want to test. So what we get here, let's say, well, remember what I'm doing here, do it in green. What I'm doing here is if I have A to the B, what would be a good letter or number? We'll use little d. I probably won't get myself into notational trouble for that. So it means I'm multiplying by a little coefficient, and I'm adding this up mod 5. So for the first column, A times B, we're just adding these numbers together, mod 5. So I get 0, 1, 2, 3, 4, and then 1, 2, 3, 4, 0, and then 2, 3, etc. And then the last one is going to also be 0 if I go all the way down to the 25th. Now, if I do this for AB squared, it's going to be, well, going by 2's now. So let's see if we can do this. 0, 2, 4. Let's see. 3 times 3 is 9. Wait. 2 times 2 is 4. Yeah, that's good. No, but of course, no, I'm sorry. It's not squaring it. See, it's easy to get this messed up. I'm not squaring it. I'm multiplying by 2. 3 times 2 is 6 reduced to 1. And then we should get a 3 here. And then we go, well, 1. I guess it's this exact same first column, but I add 1 to everything. So we do 1, 3, 0, 2, and 4. And then I add another 1 to it. Let's see if we can, I'll just say 2 and 4. And then all the way down to the bottom where I get a 1. And I'm not going to do the rest of the columns because, yeah, it's just a bunch of arithmetic and I'm just likely to make a mistake if I keep doing it. But the idea is that this would be our 5 to the 2 design. But ultimately, we might not care about these interactions because they're kind of hard to understand. So what we can do is pick an interaction like this one and say alias with factor C. So what we do is we come up with the relation that AB cubed is equal to C, or equivalently, if we move everything to the same side, we would end up with an AB cubed. Now, when we multiply, we move C to the other side of the equation, it becomes a C to the 4. I'm basically multiplying both sides of this equation by C to the 4 to get an I. And now I have a relation in my defining contrast subgroup. But what I could also do, right, is I could, I guess, take another factor D, say, and alias it with another two-way interaction. So I could alias this with D, and what I end up with is that AB squared is equal to D. If I, again, rearrange the equation, I end up with something like AB squared D is equal to I. And I have another relation for my defining contrast subgroup. I can multiply these things together and get all the other higher order ones. I'm not going to do that because it's super annoying and it doesn't matter too much. The idea is that, well, so roughly, so the main idea, right? Because I can kind of meander through this forever, but the main idea is simply I can replace those 4 columns being AB through AB to the 4th with new experimental factors to get I guess, 5 to the k minus 2 design for k equal to, I guess, in this case, 2, 3, I guess up to what? If I saturate the whole thing, I would have 6 columns. Which means on my 25 observations, if I really wanted to, I could shove 6 different 5-level factors into this design. A key thing to note is that the aliasing will be terrible. So we should assume no interactions between factors. Right, because if there are interactions, it's going to make it really hard to interpret the results that you would get out. If you had 2 or 3 or 4 or 5, I mean, not 2, but if you had 3 or more, 3 to 6 different 5-level factors that you wanted to test, and you're pretty sure they weren't going to interact with each other, then you could shove them into a 25 observations like this and do a 25 run design. All right, now there's one other really neat thing that I wanted to talk about with respect to this design. So, like I said, just before I took a little break there, we have to assume that if we have, say, 3 or more factors that we're trying to test, that they're not going to interact with each other, because we don't have the ability to test for all of those crazy interactions, and there's a lot of aliasing going on behind the scenes here, which I'm not going to write out because, again, it's a pain to write out and it's not very enlightening. But this might be reminiscent of something we saw before. It feels a lot like a, unreplicated Latin square design, right? Or a Greco-Latin square design. Way back when we discussed those designs, I said if we don't replicate our Latin square, we can test everything, sure, but we have to assume there's no interactions between the row, column, and whatever experimental factors we're putting in there, because we don't have the ability to test for those interactions. And if I were to say construct a square, and here I'm going to have A. Well, actually, why am I writing it out? I already did it, right? If I have A and I guess I can include 0 now. 1, 2, 0, 1, 2, 3, 4. No, I did it for multiplication up above. What I want to do is I want to do this for addition. 0, 1, 2, 3, 4. So if I consider, let's say, column variable A, B as a row variable, and then I consider, let's say, A interacting A plus B. Well, what do I get? I get 0, 1, 2, 3, 4, 1, 2, 3, 4, and then I add 1 to all of these, and I get a 2, 3, 4, 0, and then I add another 1 to all of these, and I get a 3, 4, 0, 1, and then I get a 4, 0, 1, 2, and a 0, 1, 2, 3, and this is a Latin square. So if I were to say, now I'm running out of room to write here in the margin, so we're just going to come down here and say, sort of, fun fact, the 5 to the, let's say, 3 minus 1 design is basically equivalent to a 5 by 5 Latin square. And what I would do is I would have factor A, B, and C, and then I would just need to say where, in this case of the blue table up here, I'm setting A, B, C to the 4 equal to the identity. Now, I could also choose other of the columns to input my factor C. It doesn't have to be the first column, the one in blue here that I highlighted. It could be one of the other ones, but the point is that what we actually have here is something like a Latin square. In the Latin square, what we would do is basically say A, B is replaced with C, and we would take all the other columns, A, B, 2, well, there's only 3 of them, so I guess it's kind of silly to write in a to put in the dots there if I'm just going to remove one element, right? And then these guys, the other columns, replaced with residuals. Right, so this is our Latin square design, where what we would be doing is we would take one of those columns and it would become our new experimental factor C. And then the other 3 columns, we're assuming that there is no interaction, so those columns can be just thrown into the residuals. And basically the point is this only works when A, B, and C do not interact. And again, when we talk about a factorial design, I'm usually saying that A, B, and C are experimental factors, where with a Latin square, we would have A and B being row and column block factors. Now, mathematically, we're doing the exact same thing. It just depends on how you interpret the results. But ultimately, it's the exact same thing. I'm just trying to figure out how to shove a bunch of factors into as small a data set as possible. And I think it's kind of neat, this connection between a 5-level factorial design or the 25-run design and the 5x5 Latin square. And then the extra fun fact is that a 5 to the 4 minus 2 design is equivalent to a Greco-Latin square. And if we were to go on, a 5 to the 5 minus 3 design would be equivalent to a hyper Greco-Latin square, and so on, because all of these columns here, AB all the way through AB to the 4th, are going to be orthogonal to each other. And because they're orthogonal to each other, they're going to correspond to orthogonal Latin squares. This is something that fails when you have, well, when you don't have prime numbers for the factor levels, and you can run into trouble. You can still get away with it if you have a power of a prime, as I mentioned. But yeah, that's more or less what I wanted to tell you about the 5-level design. Yeah, in my notes, I point out that you can consider, I guess, okay, other things to note. We can do linear, quadratic, cubic, and quartic 4th order contrasts if, let's say, a factor is ordinal. I wrote down the formulas in my online lecture notes. It's not the most interesting thing to stare at. Basically, you can think of it more conceptually, right? If I have a linear contrast at 5 levels, it's going to look like 1, 2, 3, 4, 5. If I have a quadratic contrast, and it can also go down, remember, I can always flip them by sign. A quadratic contrast would look like 1, 2, 3, 4. Oh, I messed it up. No, it is. No, I didn't. I got it right. 1, 2, 3, 4, 5. Right? My cubic in this case would have to go, let's see, 1, 2, 3, 4. I guess in this case, looking at the formula, yeah, 1, okay. It's going to look something like 1, 2, wait. 1, 2, 3, 4, 5, something kind of like this. And then the last one would be the quartic one, which is just going to look like a bunch of ups and downs. 1, 2, 3, 4, 5. So you're probably not going to see a significant 4th order contrast when you're analyzing data. You're probably not even going to see a significant 3rd order. Mostly you're probably going to see linear or quadratic, right? Linear is the most common because typically when you change your factor from small to large, you'd expect it to, well, go up or go down, the response that is. The quadratic is telling us that there's a bit of a turnaround here. It starts to go down, then it goes up, or it starts to go up, then it goes down. I think the quadratic I always think of as like over-medicating or over-watering your plants. A little bit of water is good. Well, no water is bad. A little bit of water is good. Too much water is bad, right? You drown your plants. When you get to these like 4th order contrasts, you're probably not going to see that because that's kind of like saying, okay, first we're getting a good response or a high response, then a low response, then a high, then low, then high, then low. And yeah, that's probably not going to happen in practice, but it could. You can test for it if you really want to, if you have an ordinal factor. Yes, and I think that's all that I really wanted to say about this. Yeah, so. And then we can also consider the 7-level design or the 49-run design, because you really don't want 7 cubed I mean, you really don't want 5 cubed observations because you don't really care about all of those higher order interactions. And you definitely don't want 7 cubed. That's just getting even worse. So, yeah, there's not much I mean, basically, this is the same thing. Basically is the same as above, but with 7 levels instead of 5. And the same things kind of hold here. So for example, the 7 to the k minus 2 design, which we can call the 49 run design, is equivalent to a Latin square for k equal to 3, and a Greco Latin square for k equal to 4, and so on. And I guess we can do and a hyper, we'll just say it, hyper Greco Latin square for k equal to 5, 6, 7, and 8. So why is it 8? Well, right, we would have, well, what we have is we have 49, like, let's just count it all out. The sample size is 49. Every factor, every factor we would include in the sense of like a Greco-Latin square, or every main and orthogonal component of the interaction effect. I'm just going to write every factor needs how many degrees of freedom? Well, it has 7 levels, so we have 6. And 6 times 8 is 48, which happens to be 49 minus 1. So that's the idea, is that if we really wanted to, we could take our 49 observations and we could shove up to 8 different experimental factors into them. But we have to then again assume that we're not having any interactions, or else, well, everything's going to get messed up, especially if we want to throw some of these interaction terms into the residuals. Like I mentioned above, if we have some of these two-way interactions that are completely nonsensical, we could just assume that there is no interaction and throw all of those terms into those degrees of freedom and the sum of squares associated with those terms into the residuals, which is fine unless there actually is an interaction, and then everything becomes a little bit erroneous. So you have to be a little bit careful depending on your specific experimental setting. When we do a Latin square, we assume that the row and the column are independent and also independent of our experimental factor. It may not be the case. You could have some strange orientation of your field with respect to sunlight, so it hits it in like a diagonal way, or maybe there's a slope in your field that cuts diagonally across the square, meaning that you would have an interaction between the row and the column. But if that's not the case, then we can sort of proceed as before. Yeah, otherwise there's nothing really noteworthy to do here. I guess I can also say, also, for ordinal 7 level factors, we can go up to 6th level, or 6th degree polynomial contrasts. Which you'll probably never see be significant. Which are probably never significant. But if you ever find a significant 6th order polynomial contrast, please let me know, because that would be really neat. coming from real data, of course. I could always simulate one with a significant sixth order polynomial contrast, but I just can't imagine where that would show up in practice. Again, it would basically be like your response is zigzagging up and down for every level of your factor. So I can't even imagine a scenario where that would occur, but hey, it could be out there somewhere. So let me know if you ever see one. Otherwise, yes, I have an example that we can do in R, but I think I will save that for later because it's a very short example. Instead, what I'm going to do, because we're only about halfway through, is that I want to start talking about mixed level designs. So let's get into the idea of mixed levels. So in this case, we're not going to get through all of this today. It's a little bit messy if we try to really dig into it in full generality. So I'm going to try to present them. I'm hoping that you can gain some intuition about these, but I'm also hoping that you don't beat yourself over the head trying to understand exactly all the gritty details of how they work, because it can be a little bit rough when we start talking about orthogonal arrays, which we're going to do right now. But first, the rough idea. So the question is, how do we combine, let's say, 2 and 3 level factorial designs efficiently and, let's say, 2 and 4 level designs as well. So that's probably something that you might have thought about when we were talking about 2 to the k designs and 3 to the k designs, is that, well, my factors aren't always all going to have the same number of levels. Now, at least the 2 to the k factorial design is a very useful tool. It's very common to have basically a lot of binary factors. It's either I apply the treatment or I don't. I either give you pill A or I don't, or give you pill B or I don't, right? Or I take chemical A and drop it on my soil or I don't, or take chemical B or don't. And similarly with the 3 level, you can think of it as a typical place where that's going to arise will be having, let's say, 0 small and large applications of some medicine or treatment or chemical or whatever. So again, a 3 level might be I have a sort of no medicine or a small dose or a large dose of medicine, and I want to know how that affects the response, whatever I'm trying to measure. But it is the case where you could very well have mixed 2 and 3 level factors. You can sometimes have mixed 2 and 4 level factors, and the 4 level factors are actually quite confusing. But the nice thing about a 2 and a 4 level factor is that you can carefully kind of condense them together in order to not have a massive sample size. So what I'm going to do is an example really fast. So let's talk about the naive way. The naive way would be if I have, let's say, a 2 to the 3 and a 3 to the 2, is to basically just, well, mathematically tensor product them together. And what I mean by that is that if you have a 2 to the 3, you basically have something that's going to look like ABC, minus, 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 plus, minus, plus, minus, minus, plus, 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 minus, minus, plus, minus, plus, 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 minus, and a plus, plus, plus. Excellent. So we would basically have these 8. And if we had, I'm going to need new letters. I guess we can do D and E and try not to get too confused about it. If I have my 3 to the 2 design I would have something that looks like this, where I would have 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, and I would have 9 observations. So what I could do is just multiply these two things together and get something. So if I sort of take these, I can multiply them together and get 72 observations of the form A, B, C, D, E, where what I would do is I would have, for every setting in the table, let's say DE, so for every choice here and here, I would have an entire 8 observations of minus, 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 all the way down to plus, plus, plus. So I would do this, say, for, let's say, 0, 0, and then I would do it again for 0, 1, and I would have those 8 treatments in A, B, and C repeated. And this would take a total of 72 sample points to be able to do it this way. But the question is, can we get away with a smaller sample? Because once again, the same sort of reasoning applies here, which is, okay, I'm not looking for high order interactions. I don't really want all this extra junk in there. I'd like to just have a smaller sample size. Can I get away with it? Is there an efficient way to do this without having some horrible conflict of aliasing relations and confounding and all that headache that can come in? So that's really the goal, because we can always come up with, like I said, kind of the naive way to do it, which is we take our 2 to the k and we take our 3 to the k prime, say design, and we multiply them together, or the same with a 4 level. We're just going to get a really big sample size and it's going to be annoying. So that's really the goal, is that can we somehow do this more efficiently? And that's where we get the idea of a symmetric orthogonal array. So enter the idea of an orthogonal array. And specifically here we have the mixed level. So this is a mathematical combinatorial object that people like to study. And basically we have, I'm going to write it out sort of carefully using the definition in my lecture notes, which is given S symbols, these are just going to be our factor levels, 1, 2, up to S. Actually, I think this is the symmetric orthogonal array. We haven't gotten to the mixed level one yet. Sorry, I got my... This is the definition. This is not a mixed level array. This is a symmetric array. And these can be thought of as the factor levels. They're really just symbols. So again, it's like I kind of said when we did Latin squares, we talk about Sudoku puzzles. Like if you solve a Sudoku puzzle, which is just a Latin square with some extra restrictions, you're just putting in numbers 1 through 9. But ultimately, the numbers have nothing to do with anything. They could be symbols, they could be letters, they could be whatever you want. So here, the idea is that I have S symbols, which are going to be my factor levels. Now, we need and given S symbols, and let's switch back to black, and T, an integer, greater than 0, which is going to be the strength of the table. We haven't talked about that, but we'll get there. We'll call it the, well, maybe not the, which is the strength. Right. And n by, yeah, so right, yeah, given this and that T, which is the strength, then and capital N, N by M orthogonal, I'll just write it all out. Make sure I don't miss any steps here. Orthogonal array of strength T with strength T is denoted to be O, A, N, S, M, T. Isn't OAN that like crazy news network or something? I forget. I feel like that showed up somewhere recently when people complaining about it being like some absurdist news thing. But anyway, side tangent. That's our notation. It's an orthogonal array, N rows, S symbols, M columns, and strength T. So what does all this actually mean? Well, the idea is that, so this is an N by M table with entries 1 through S, such that every set of T columns will have every combination of T symbols, I guess, occurring an equal number of times. Equal number of times. Cool. So what does that mean? Okay, so what in the world does this definition mean? Well, perhaps the best way to do is an example of something we've already seen. So an example is the 2 to the 4 minus 1 design with I equal to A, B, C, D. Okay, so this is just 2 to the 4 minus 1 fractional factorial design with a single defining, well, a single relation in the defining contrast subgroup. We've aliased A, B, C, D with the identity. And the idea here is that if I were to consider this design, I would get something that looks like this. So I would have A, B, C, D. Those are my 4, my 2 to the 4, right? My 4 factors. And then I would have interactions AB, AC, AD. And if I consider the aliasing relation, remember each of these is going to be paired up with one other term. I'm going to get a BCD paired with A. I'm going to get an ACD paired with B, and ABD, ABC. So all of my main effects are paired with a third order interaction, and all of my two-ways are paired with another two-way. So AB is with CD, AC is with BD, AD is with BC. And of course, there's like one other column that I'm not adding here, which is as ABCD, which is aliased with the identity, so it's all going to be ones. So if I put this all together, what this design would look like, using my dots for zeros and my, I guess, pluses for ones or something, I get dot, 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 plus, 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 plus. Though I think I should space these out a little bit better because that's terrible spacing. We'll do dash, 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 plus, 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 and plus. Okay, the next one is dash, dash, plus, plus, dash, dash, plus. Then we alternate every 1 plus 1 plus dash plus, I cannot get this one, dash plus dash plus. All right, and then what is D? So D in this case is going to be dash plus plus dash, nope, yes, and then plus slash slash plus. All right, we're almost there. We have AB, which is the interaction between A and B. That one, you can get these other ones too, right, by effectively extending the table and considering these aliasing relations. In this case, I'm just trying, I already kind of skipped that step just because I don't want to have to write out 64, well, not 64, 2 to the 4, 16 columns and try to delete a bunch of them. So this is dash, dash, plus, 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 dash, dash, and we have dash, plus, dash, plus, plus, dash, plus, dash. And the last one is, 1, 2, 2, 2, 1. 1, 2, 2, 2, 1. Okay, now we have our table. So this is our giant table, right? We would have our observations y1 through y8, I guess in this case. Now, this table is an example of an orthogonal array. Yeah, so in this case, this table, this is an orthogonal array with a total of 8 rows. The number of symbols is 2, right? I have 2 different symbols, minus and plus. So I'm going to get S is equal to 2 in this case. I have 7 different columns. And then the question is, what is the strength of this? So again, the strength says that for any T pairs, or not pairs, for any collection of T columns, I should see every possible symbol combination repeated an equal number of times. So, for example, if I took T equal to 2, I could look at AB. So here I see minus minus occurs twice, minus plus occurs twice, plus minus occurs twice, and plus plus occurs twice. And similarly, if I take any 2 pairs of columns here, I should see 2 minus minuses, 2 minus pluses, 2 plus minuses, and 2 plus pluses in any pair of columns chosen. So the table strength has to be at least 2. Is it 3? So in that case, I would have to see every combination of the symbols of in 3 columns. So for example, if I take A, B, and C, I have the all minuses row, it occurs once. I have minus, minus, plus, it occurs once. I have all the other triples that occur all the way down to plus, plus, plus that occur once. And we would note that if I choose any other collection of 3 columns, I would have the exact same thing. That is, every triple of symbols, minus, plus, minus, plus, minus, plus, will occur exactly once. And what that means is that we have a strength 3. This is strength 3 because every choice of 3 columns has every combination of minus and plus occurring once. And what we see is we can't have a strength 4. Well, first of all, the easiest way to see that it can't be strength 4 is the fact that there are 16 different ways, that are 16 different choices for minus, plus, minus, plus, minus, plus, minus, plus. And I only have 8 possible rows, so it's just doesn't even work one bit. But we could also just note that, for example, if I take A, B, C, and D, I know that the product of A, B, C, and D has to be, I guess, 1 or whatever. They have to multiply together, which means I have to have an even number of pluses and an even number of minuses in the collection of columns A, B, C, and D. What that means is that, well, I can either have all minuses or half minuses, half pluses, or all pluses, but I can't have 1 and 3, right? I can't have 1 minus and 3 pluses. Therefore, we can't possibly have strength 4. Now, this is a useful thing to be aware of. The idea of strength is kind of saying how many different, well, it's kind of generalizing this idea of orthogonality, right? If I have 2 columns, they're orthogonal if every combination of symbols occurs an equal number of times. This is extending it to triples and so on. It means that if I want to look at factor A, B, and C, or B, C, and D, or any 3 choices here, every possible combination will be tested. And that's nice. What we don't have is that for 4, we don't have every possible combination of A, B, C, and D being tested, but for any 3 of those, we have every possible combination being tested, right? And typically, right, we want to test all the possible combinations of, say, 2 or 3 or more factors that will allow us to get better results in our testing. So that's why typically we want an array that has a higher strength, but strength is going to be very closely related to the idea of resolution in a design. So let's look at that. So this is going to be a note on, well, first of all, we're going to note this is strength 3, and we'll also note that this design up here is a resolution for design. All right, and we talked about before that we want the resolution of a design to be higher, but not necessarily too high. If it's too high, that means we probably have too large of a sample size that we don't need. So again, there's always a balance here. How much data do we want to test what we want to test without getting all this extra factors in there that we don't really care about testing? So oh, that's right. Yeah, there was a claim in the text by Wu and Hamada that strength is equal to resolution minus 1. But yeah, we have to be a little bit careful when we do that, because that's right, there is one subtlety that I needed to point out here, and that's, hold on. Yeah, I missed one quite a little subtlety here, which is that for this table, we really want to consider the main effects. Because that will change the strength will change depending on if we include more of these interaction columns. And that's something that I forgot to mention when I was excitedly talking about this just a minute ago. So if we consider the column A, B, and A interacting with B, there we don't have every combination. So in fact, this is still an orthogonal array of strength 3, but that's just for the green box. Right, basically, this works for main effect columns, but not when including interaction effects. Yeah, I told you, these things can get a little bit tricky, right? And what I was getting at there is the fact that every combination of like I said a little bit earlier, every choice of 3 of A, B, C, and D will see every possible factor level combination. But if I choose columns A, B, and A interacting with B, I don't see every possible combination. So I needed to be very specific and say that this orthogonal array here is corresponding to our 4 main effects and not the entire table, which actually makes me think that I should probably change the notation here, apologies for that, to be a 2 to the 4, because I have exactly 4 columns with my symbols such that every pair works. Yes. If I were to include the rest in the table, it would then be strength 2, because I think every pair should have an equal combination of all the minus, 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 plus, plus, minus, plus, plus, but every 3 will not have every possible combination. The counterexample, of course, being that A, B, and AB do not see every combination of symbols. Yeah, these things can be a mess, right? Oh, yes. So in general, we have this idea that we can consider our factorial designs like a orthogonal array. And then the question is, well, why are we doing this? We're doing this because it's going to help us understand mixed level designs. Well, I should say we also have. So we also have the case that a 3 to the k minus q design could be thought of as an orthogonal array with, I guess, 3 to the k minus q rows. And then it depends on, again, if we're thinking of just the main effects in this case, we would have something like, well, it's going to be another 3 to the k minus q, I guess. 3 to the k columns for the main effects, and then some strength t. So it's a little confusing, but this is the rows. This is the symbols. This is the number of factors. And this would be the strength, which I believe in this case, because we're not including the interaction terms in our orthogonal array, would then be something like the resolution minus 1. All right, so the last thing I'm going to mention today, and we'll be we'll be trying to apply this in practice in the next lecture, is to define, orthogonal array again. But in this case, we're going to be doing mixed levels. All right, so in this case, what we're going to say is, now, given symbols, this is always a mess, given symbols S1 through S, say, gamma, for lack of a better index, that is, we're going to have 1 through S1 and 1 through S2 and so on. Just to indicate, we might have something like S1 is equal to 2 and S2 is equal to 3. So I have some 2-level factors and some 3-level factors, for example, E, G. Okay, so given basically different factor levels is what I'm trying to say by these S's. Oh yes, and M equal to the sum. This is the total number of columns, I, from 1 to gamma of mi, where M is equal to the total columns, and mi is equal to the number of columns for, we'll say, factor level Si. Yes. So if we have that, oh, and then of course we're going to have and strength T again, then what we have is we have our orthogonal array OA of n, and then we're going to have something like S1, M1 through S gamma, M gamma. I'm going to give an example. So this is, yeah, stick with me for just a minute longer, right? And strength T. And the idea is that where, so this is a table, capital N by M, such that every combination of T T symbols, I should say, occurs in every T group of columns. All right. So yeah, that's kind of well, an annoying thing, but we can do a quick example just to try to show you what I mean. Yes, and we'll do an example kind of hinting at where we'll be going next. So an example is an orthogonal array with, what is this, 8 rows, 4 columns that have 2 levels, 1 column that has 4 levels, and a strength of 2. And what that's going to look like is going to be, well, something that's going to look like this. We're going to denote it A, 1, 2, 3, 1, 2, 3. And in this case, what we have is we have our observations y1 through y8. And then A is going to be my 4-level factor. So it's going to take on the values 0, 1, 2, 3. And then we're going to repeat. And in my example, I repeat it in reverse order, 3, 2, 1, 0. So A is a 4-level factor, whereas my 1, 2, 3, and 1, 2, 3 are binary factors. So we're going to have them be dash, 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 plus, 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 plus. The same thing I write every time. Dash, dash, plus, plus, dash, dash, plus, plus. Dash, plus, dash, plus, plus, dash, plus. And lastly, we have a dash, plus, plus, dash, plus, dash, dash, plus. Cool. So what is going on here? Well, the idea is that any pair of columns, we have strength 2. So that means that any pair of columns should see every symbol combination occurring an equal number of times. And that we saw already with the 2 to the, this is a 2 to the 3 design in here. I have 4 columns, which is why it's a 4, because I'm including the 3-way interaction term. But the idea is that any pairing of these columns will have equal number of minus, 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 plus, plus, minus, and plus, pluses. But I also get the same thing occurring with column A. So an example is that if I have just A and 1, Well, I have every combination of 0 and minus 1 occurs once, and I have a 0 and plus occurs once. I have a 1 and a minus, and I have a 1 and a plus, etc., occurring once. So that means that this is why it's an ideal thing to have, right? What I'm saying is that for my factor A, which has 4 different levels to it, every choice of A, every setting for A, and every setting for 1, 2, 3, and as a consequence, the interaction term 1, 2, 3, are going to occur exactly once. It's going to be tested exactly once in my design. So I have an observation 1 through 8 that's going to have one of all possible combinations tested basically between A and factor 1, A and factor 2, A and factor 3. And note that I only have 8 observations here. So here's the takeaways for this example. Call it the takeaway. Well, one is that every combination of levels for A and 1, 2, 3 are considered. And furthermore, this is done with 8 observations, which is not 4 times 2 to the 3, or 4 to the 1 times 2 to the 3, which would be 4 times 8, which is 32. So what I'm trying to get at is the fact that I can test my 4-level factor, I can test 3 binary level factors, and I can do so in an array or in a design table here that only requires 8 observations rather than 32, which would be the naive way I talked about at the beginning, where I just take my 4 to the 1 and my 2 to the 3 and I cram them together. Now, I could consider, say, a 2 to the 3 minus 1 if I wanted to do a fractional design. That would still take 16 observations. Here, I managed to cram them all into 8, which is kind of neat. Right? It basically means I can test 4 different things, A, 1, 2, and 3, on just 8 different observations, and that's very efficient. Again, there's higher order interactions that we're kind of neglecting and we're assuming are not going to cause any trouble because we don't have the data to test for them. But again, that's just our trade-off. We either have to collect more data to test for the crazy interactions between A and 2 and 3, for example, or we could ignore all that and just have a small data set and hope that there aren't any higher order interactions. Right. So I think that's probably, based on the time, about enough for today. What I'm going to do in the next lectures, we're going to talk about specifically 2 and 4 level designs and 2 and 3 level designs because they're the most common type of mixed level factorial designs that you might see in practice. And that should give us a bit. We'll also do some R examples just to maybe help make some sense of this. And then we can move into some even cooler stuff with, I think Plackett-Bergman comes after that. So we'll stop for now. We'll get ready for some more mixed level designs, but that will be occurring in the next lecture. So see you there.